Okay, so in the previous video we looked at what happens when we add heat and there's a change in temperature. Now we're going to look at what happens when we add heat, but we're not going to play around with the temperature. We add really it's add or remove heat, right? But we're not going to play around with the temperature, right? Or we're not going to increase or decrease the temperature. We're going to look at that phase change. Okay, so there is no temperature change occurring when there is a phase change. And if you remember, well, what are phase changes? When I go from solid to liquid, right? And I go from liquid to gas, and vice versa, right? So this is my melting slash freezing point. This is my boiling point slash condensation point. Okay, when I add heat, right, versus when I remove heat. Okay, so the energy involved in a phase change depends on two major factors. The number of bonds, which has a direct relationship to the mass of the object or the substance, and then the strength of the bonds, which has to do with the molecules themselves. Okay, so the heat required to change the phase of a sample of mass m is given, right, there's really two equations. Right, something called M, oh sorry, I was doing LF first, not LV. LV is the second one. So MLF, right? So LF stands for latent heat of fusion, okay? And this occurs at the melting slash freezing point, okay? Freezing, fusion, right? When you freeze something, you fuse things together. The second equation, we're just changing the subscript of L, right? So it's MLV, and this is what we call the latent heat of vaporization. Okay, and this occurs at the boiling slash condensation point. Right, so if you want to think about it, latent heat of fusion, when you go from solid to liquid or liquid to solid. Latent heat of vaporization, when you go liquid to gas or gas to liquid. Okay? Now, pull my purple pen again. I really like using purple in these videos. So there is more energy required for a phase change as compared to that of a temperature change. Okay? Now, why is that? Because you're breaking these bonds apart, right? And so, remember, solid looks like this. It's this nice 3D structure, right? And so these bonds are nice and tight. And what we want to do is as we do the latent heat, we want to break these bonds and let these particles start to move, right, to get into a liquid. Okay? So we have to really add more energy to that process than we would doing a temperature change. So more energy, right, is required to heat a material as compared to cooling it. Boiling and melting are heating processes, while condensing and freezing are cooling processes. Heating means you're going to have a positive Q, right? I'm adding heat to the system, so I'm increasing the heat. Cooling, I'm going to have a negative Q. Okay. Now, oftentimes, if you do a lab associated centered around this, this is one where you would have a beaker full of water and ice, and you take the temperature every so many minutes or seconds or whatever, and you end up plotting out a graph that looks very similar to what you see here to the right. And what happens is when you have a slope line, that means there is a temperature change. Okay, so there's a delta T, there's a delta T. But notice that when you have the phase change, when you have ice and water, water and steam, this says stream, but it's just say steam, not my graph. Okay. Once you have ice and or that water or ice converting to water, right? You have this. You have a there is no temperature change. And the same thing when you have water and steam together. And so one thing to know is that you do have to add more heat to go from water to steam than you do to go from ice to water. Okay, so we could do that same process of thermal equilibrium when we look at the phase change. Okay, and so that's what we're going to do here in this problem. So we're going to have 3 ice cubes chilling a soda at 20 degrees Celsius with the mass of the soda being 0.25. The ice is initially at 0 degrees Celsius. Right, it's ice. And each cube has a mass of 6 grams. Assume that the soda is kept in a foam container, Chick-fil-A cup, Sonic cup, right, so that the heat loss can be ignored. And assume the soda has the same heat capacity as water, which is 4186. Find the final temperature when all the ice is melted. Okay, so what we need to do, you can really do a couple things here. You can look at how does when I add heat to the system, how do I change and so forth. But what you're really doing is that the ice is going to gain heat, right, and the soda is going to lose heat. Okay, so it's the same thing we did before, but what we have to do is, right, we have a phase change we have to deal with, as well as a temperature change. Right? And then for the soda, we only have a temperature change, so it's going to lose that MC delta T worth of, right, of heat. Okay. Now the ice side is pretty easy because the initial temperature of ice is 0. So in my equation, that's just going to be my final temperature. But on my soda side, I've got to expand out to be my TF minus TIS. Okay. Do the same thing like I did before. So I have MSCS TF minus or plus MSCS TIS, right, equals this up here. Get all my final temperatures on one side, everything else to the other. So one thing to note that if the ice started at a different temperature, we would have to add that part into this, right? But because the initial temperature of ice is 0, we can just eliminate that part of the equation. And so I'm going to subtract that. Yes, so I'm going to subtract the MILFI over and add over the MSCSTF, right? So I'm going to do some couple steps in one shot here. So I'm going to do MICI, right, plus MSCS times TF, and that's going to equal MSCSTIS minus MILFI. Okay, and so my final temperature, as you can see, it's going to look very similar to what we had before. It's going to be MSCSTIS minus MILFI, right, divided by MICI plus MSCS. Right, and now I can just plug in my numbers. So the mass of the soda is 0.25, right, 4186. They tell me the specific heat is the same as water, and it starts out at 20 degrees minus. Now, the LF for water is 333,400. And it's going to be joules per kilogram is our SI unit. So that's going to be, now you do have to be careful, it's 6 grams, that's 6 times 10 to the negative 3, but there's 3 ice cubes, so that's 18 times 10 to the negative 3 times that 334,000, right? Now I can do a little bit of algebra here because CI and CS are the same, so it's going to be that 18 times 10 to the negative 3 plus 0.25 times 4186, right? Because they told me that the soda has the same specific heat as water, and the temperature, the final temperature, is going to be 13.3 degrees Celsius. So one thing you note is the ice went from 0 degrees Celsius to 13.3 degrees Celsius. The soda went from 20 degrees Celsius to 13.3 degrees Celsius. So here we gained heat, here we lost heat. Okay? So the hotter soda sped up the particles in the colder ice. Okay? Now, there is one other phase change that, we talk about boiling point, melting point, and all that. But there is a process called sublimation. So sublimation is the phase change from solid to vapor, right, without having to go through liquid. Okay, so this is the reason why dry ice looks like it's foggy, right? At Halloween time, it's like woo, right? And so people put the dry ice in water, and it kind of spews out as fog, right? Because dry ice is just simply solid carbon dioxide, right? And it doesn't necessarily go to a liquid phase. It goes from solid to gas, okay? And so the amount of heat transferred during sublimation, so the equation just simply goes from being MLF to MLV to just mean MLS. So there is a latent heat, what is called a latent heat of sublimation as well. And if it's not given to you, you can look it up, but you may have to solve for it. Okay. So the last thing that we're going to talk about, because really this is 8.2. So the last thing we're going to talk about in 8.2 is how do we transfer that heat, and how does that affect our everyday life?